Today's lecture, we'll see some problems on DFT. Let us take the first question, that is x of n is equal to 1, 1, 1, 1. So the signals will be something like this. So x of n equal to 1, 1, 1 means the arrow here means the point where it is 0, the n equal to 0 point. For instance, just I am giving you an example. If I am giving a signal like this, x of n equal to 1, 2, 1, 1. That means my 0 point n equal to 0 is having value 2. So for that question, your signal will be like this: 2, 1, 1, 1. So this is just an example. So in our question, the 0 point, the signal is starting from n equal to 0. You don't have anything before that. It will be 0, 1, 2 and minus 1. In our case, our signal is 1, 1, 1, 1. Now the question is to find 8-point DFT of x of n. So first part of the tackling this solution is, question is, you have to write the equation for DFTs. So x of k is equal to summation n equal to 0 to n minus 1 x of n e raised to minus j 2 pi n k by n. K goes from 0 to n minus 1. And since our signal question is having only 4 samples, there are only 4 ones, rest there is nothing else. So in order to apply it in our equation, what you will do is 0 padding. That is in order to make it equal to size n. So that is we have to make it. The question is to find 8-point DFT, but we only have 4 points. So our new x of n will be 0 padded to make it size 8. So this will be our new signal. Next part is we are going to apply it in the expression. So in this particular question, this is just your first question. So we are going to do it by substitution method. That is, we'll just substitute the values of, we'll substitute x of n, and then for each case we'll separate out the values individually, step by step. In the later questions, we'll see how this can be tackled in a much easier way. So for now, we'll see how it is done in sample substitution method. That is, x of k equal to summation n equal to 0 to n minus 1 x of n e raised to minus j 2 pi n k by n. That we are going to substitute. So x of k equal to summation, our n value is 8. So your equation is going to be n equal to 0 to 7 x of n e raised to minus j 2 pi e raised to minus j 2 pi nk by 8, and k tends from 0 to 7. Now let us find k equal to 0. That is, what is x of 0? The zeroth sample. So x of 0 will be, that is k equal to 0. So when k equal to 0, you don't have to worry about the e raised to j terms, because k equal to 0 means e raised to j part will be equal to 1. So you just, now I'm going to open the summation. So it will be 1 plus 1 plus 1 plus 1 equal to 4. Similarly, x of 0, x of 1 will be, that is k equal to 1. That what I'm going to do is, I'm going to just open the brackets. So it will be small x of 0, that is your time domain signal. So x of 0 into e raised to j 2 pi, n value is 0. So e raised to j in the first sample is not relevant here. So it will be the first sample x of n, that is 1 plus n equal to 1. So when n equal to 1, x of n is again 1. So it's 1 into e raised to minus j 2 pi n is 1. 1 into 1 by 8 plus the third x of 2, n equal to 2 case. So in that case, it will be 1 into e raised to minus j 2 pi into n equal to 2. 2 into 1 by 8 plus the next sample 1 into e raised to minus j 2 pi into n equal to 3. 3 into k is 1 by 8 plus rest all are zeros because x of n equal to 0 after that. That is, I can write it as 1 plus minus j pi by plus pi by 2 plus e raised to minus j 3 pi by 4. That's it. Now how will I find the values of this one? For that I have to find 1 plus e raised to j theta is cos theta plus j sin theta, or e raised to minus j theta is cos theta minus j sin theta. So it will be cos pi by 4 minus j sin pi by 4 plus cos pi by 2 minus j sin pi by 2 plus cos 3 by 4 minus j sin 3 by 4. So this is how you find the solution. So if you look in some other questions, they will tell you to plot the amplitude and the magnitude. That is known as the magnitude and amplitude, the magnitude and the phase. So this is known as the magnitude spectrum and phase spectrum. So in that case, you have to find the magnitude and phase of each of the samples that you get. So in this case, x of 0 is, for x of 0 is a real number. So the magnitude of x of 0 is going to be 1 and the angle is going to be 0 in this case. So the final answer is left as a homework. So you will get something like this, x plus jy form. That is, you will have to find out you'll have to find the magnitude and phase of this thing. So how do you find the magnitude and phase of this one? That is, magnitude is, so magnitude of x of 1 will be root of x square plus y square, and the angle of x of 1 is tan inverse y by x. So find this solution and then find the magnitude and angle. Similarly, let us go to the next sample, x of 2. So x of 2, again, the first sample will be, there will be no influence of e raised to j because n equal to 0. So it will be whatever is there in x of 2 will be, small x of 2 will be your answer. So that will be 1. 1 plus, next will be x of 1, that is 1 into e raised to minus j 2 pi n is equal to 1. 1 into k is 2 by 8 plus the next 1 into e raised to minus j 2 pi into n is equal to 2 into 2 by 8 plus 1 into e raised to minus j 2 pi into n is 3 into 2 by 8. So likewise, as previously told, find the answer. Likewise, you have to find for x3 till x7, capital X of 7. So these will be your DFT samples. Now if they are telling you to plot the magnitude and phase spectrum, what will you do? That is, you have already found out what is the magnitude and angle. If you have found out, then you just have to plot it. The plot will be like this. This will be the format of plotting. That is, this axis will be k, and you will have k from 0 to n minus 1, and this will contain the magnitude, and it will be small impulses, something like this. Just an example will be like this. This will be your magnitude spectrum, while your phase spectrum might also be something like this, where here you have the angle of x of k, and that also will be from 0 to n minus 1, something like this, maybe just an example. So this is how you need to tackle this particular solution. So remember, in this question what we have done is, always first write your expression for DFT. Then if your DFT n value is greater than the length of the signal, you have to zero pad it to make it equal to the length of the DFT that is asked. Next, let us go to the next question. That is, x of n is equal to delta of n. Find the DFT of that. X of n is equal to delta of n. Find the DFT. So delta function is only present, a discrete delta function is only present at the 0 point at n equal to 0, and the value is equal to 1. So now I'm going to substitute in the expression summation e raised to minus j 2 pi nk by n equal to 0 to n minus 1. But here there is no meaning of summation, because your x of n is defined only at 0 point. So your answer will be equal to, since x of n is equal to 1 at 0 point, and at only 0 point, at n equal to 0 only, you have a value. So your final answer is going to be equal to 1. Similarly, let us go to the next question. That is, x of n is equal to, find the endpoint DFT of x of n equal to delta of n plus delta of. So how are we going to do it? So again, the same method. So here your x of n will have will look like this. X of n, and at n0 you have another point, each is equal to 1. So substituting it in our expression for DFT, what you are going to get is n minus 1 x of n e raised to minus j 2 pi nk by n. So in our previous question, we saw this to be equal to 1 for 0 to, you have to when you plot it, it's not just 1, it is for k equal to 0 to n minus 1, the value is equal to 1. Similarly, here, how will it look like? X of k is equal to summation x of n e raised to minus j 2 pi nk by n. So your answer is going to be only at points n equal to 0 and n equal to n0 you need to worry. So here x of n e raised to minus j 2 pi nk of n, the first n equal to 0 you already found out it to be equal to n minus it to be equal to 1. And the next thing, next part is only at n equal to n0 you have a value. So at x of n will be equal to 1 there, and the answer is e raised to minus j 2 pi, and this to be equal to n equal to n0. For k equal to 0 to n minus 1 you have this answer. The next question, find the DFT of x of n equal to a raised to n, a less than 1. So here you would have seen similar signals in the previous semester when you are doing Z transforms. That is, find the Z transform of a signal of such forms. So this looks like a geometric progression. We have to look at the expression for a geometric progression to tackle these kind of questions. So sum to geometric progression is, if your ratio between two consecutive terms is r, will be 1 minus r raised to n by 1 minus r. And if there is a factor, extra factor, you write it as a. So this is the general form of the sum to n terms of the geometric progression. So how will we do it? So in our expression for DFT, you have x of k is equal to summation n equal to 0 to n minus 1 x of n e raised to minus j 2 pi nk by n. It can be written as summation n equal to 0 to n minus 1 a raised to n and a into e raised to minus j whole raised to n. So this is a sum to n terms of a geometric progression. So this can be instead of r you have this to be your r. So it will be 1 minus a into e raised to minus j 2 pi k by n whole raised to n by 1 minus a into e raised to minus j 2 pi k by n. So that is equal to 1 minus a raised to n e raised to minus j k by 1 minus a. So this is your final answer. Next, let us find the IDFT. So the aim of IDFT is to find out the original signal x of n, the time domain signal x of n, given the DFT samples. So in this question, we don't have to think about the concept of zero padding, because zero padding we only need to do when we have to find out how many point DFT we have to find out. Here the DFT is already given to us, so we don't have to think about how many zero paddings and all. So here it is 4, so it is already understood that this is a 4-point DFT. So all we need to know is, we now know, all we need to know is the expression for IDFT, and we know that n equal to 4. So in our case, n equal to 4. So let us look at the expression for IDFT, that is this particular expression. So we are just going to, we just need to substitute this one into this particular expression and find out the solution. So that is, in our case, it will be 1 by 4 into, we just have to substitute summation k equal to 0 to n minus 1 is going to be 3 x of k e raised to j 2 pi n k by n is going to be 4. Now just like your previous case, you have to find out samples from here. Remember, we are finding the time domain signal, so n equal to 0. Unlike the previous, and finding the DFTs, we have to put k equal to 0 and find out for each ends. So only the change is here we are taking in the reverse way. So you have to find the samples for x0 to x3. This will be your uh, IDFT, IDFT of x of k, or the time domain signals. Now, so find the solutions. So we have to find out. Just substitute the exactly same method, and you have to, whenever you find e raised to j, the method is you have to find out e raised to j. You have to represent e raised to j as cos theta plus j sin theta, or e raised to minus j is cos theta minus j sin theta. Expand and find the solution. You are going to get real numbers. You will never get, in this case, you are not going to get any uh, imaginary numbers. Let us go to the next question. So this is an important question to understand the concept of frequency resolution. So in that, you would have heard of time domain time signal resolution. That is, it comes in sampling. That is, when you are sampling a signal in the time domain, or x of t, given a continuous time signal x of t. If you want to sample it, what you are going to do is, we are going to take samples at some duration. So this is known as, this particular duration is known as the sampling period. That is t, sampling duration. And 1 by t is known as the sampling rate or sampling frequency. So now, if I am getting like this, so let us assume that this is my x of n. So it is like this. So when I am connecting the dots, I am going to get a approximation of x of t. I'll call it as x tilde of t, an approximation of my signal, time domain signal. Instead, what will I get if I am sampling at better rates? That is, I'm taking more samples in between. You can see it here itself. If I'm taking more samples here itself, when I'm connecting the dots, I'm going to get a better uh, better estimate of x of t. That is, I'm able to get back my original signal with a very less error. So that is the advantage. So that means that that particular signal, discrete signal, has more resolution. That is, signals with more samples per unit time. Signals with more samples, or the sampling rate is high. Those kind of signals are told to be are called signals with high resolution. So that concept is same as what you see in your image processing. That is, image is a two-dimensional signal, and you would have heard of resolution of a picture. That means number of pixels per unit image, unit area. So in that case, the number of pixels, if it is more, means more information is contained in that region, and but the amount of storage space is more. That is another part that you will understand later. But here more samples means more the resolution of the image and the clarity of the image is high. That means it's the signal, more information is contained, and say we are able to reproduce the signal or actual image better with more number of uh, samples. So this is an example of a 2D signal. An image is an example of a two-dimensional signal. And this concept is same. Resolution concept is same for your 1D signal and your 2D signal. More number of samples means higher the resolution. Now let us go to the frequency resolution. So in frequency resolution, in IDFT, in DFT, we are told that DFT is actually the sampled version of your DTFT. So DTFT is something like this. So the sampled version is something of this sort. So in frequency resolution means, and this is n, 0 to n minus 1. So what happens if I am increasing the number of samples in the frequency domain? That is, I'm making the n value very large. That is, large number of samples are taken between 0 to 2 pi. If I'm taking large number of samples in the range of 0 to 2 pi means I'm able to, if I want to reproduce the original spectrum, I'm able to do it better. So that is the advantage. So if I'm taking more number of DFT samples, better is the frequency resolution. More the value of n, better the frequency resolution. So this is what you will see in this particular example in your first reference by the ProArchis, digital communication, digital signal processing by ProArchis. In that, you must have a look at how frequency resolution is increasing by increasing the value of n. So in practice, even if you are given a signal of x of n is equal to 1, 2, 3, 4, and if they are telling you to find a 128 point DFT, you have to do is you have to add 124 zeros and add 128 124 zeros to make it once, and to make it equal to 128, and then do your DFT. So this is what is happening in practice. Even if the actual time domain signal is very length, they will ask you to do a higher point DFT so that you will get a better actual information of your frequency content. So that is the concept of frequency resolution. That is, higher the number of higher the value of n, higher the frequency resolution. That means you are going to get a better estimate of the actual spectrum of the signal. So that is what is the role of the n value, capital N value. So this concept you will get a better picture by looking at the example given in 7 point in textbook 1, this particular example. Just have a look at it and you'll get a idea of frequency resolution. Okay, so that is it for today. Thank you.